Imagine standing at the foot of a mountain that would make Earth's mightiest peaks look like mere hills. Mount Everest, our planet's highest point, would be dwarfed by the colossal formations on Mars. These Martian mountains tell a story of ancient volcanic activity that persisted for millions of years, unconstrained by tectonic plates that fragment Earth's surface. Picture yourself gazing into a canyon so vast that our own Grand Canyon would appear as nothing more than a slight crack in comparison. This is Mars, where geological features stretch beyond human comprehension and hold secrets of a distant past when water flowed freely across its surface. Today, we embark on an extraordinary journey across the red planet's most remarkable features. We'll traverse enormous valleys carved by ancient rivers, stand in awe before dormant volcanic giants, and uncover evidence of a time when Mars may have harbored conditions suitable for life. The surface of Mars serves as a time capsule, preserving billions of years of planetary evolution in its rocks, minerals, and dramatic landscapes. We'll explore how these massive formations came to be, examining the forces that shaped Mars when it was young and more geologically active. From the towering heights of Olympus Mons to the depths of Valles Marineris, each feature tells part of an epic tale about Mars's transformation from a warm, wet world to the cold desert planet we see today. This isn't just a story about alien geology. It's a window into what our own planet's destiny might be, and perhaps a glimpse of where we might find traces of ancient Martian life. If you're captivated by the mysteries of space exploration and eager to delve deeper into the cosmos, join us at Exploring the Universe. Every week, we venture further into space, unraveling the secrets of our solar system and beyond. Together, we'll explore the final frontier, one celestial body at a time. Standing as the undisputed titan of the solar system, Olympus Mons redefines our understanding of volcanic formations. If you were to stand at its base, its summit would vanish into the Martian sky, a sight that would have been even more dramatic when Mars possessed a thicker atmosphere. This sleeping giant rises an astonishing 21.9 kilometers above the surrounding plains, with a base spanning approximately 600 kilometers in diameter, roughly the size of the entire state of Arizona. The formation of Olympus Mons tells a fascinating story of sustained volcanic activity uninterrupted by tectonic plate movement. Unlike Earth, where volcanic hotspots are constantly moving as plates shift beneath them, Mars's stationary crust allowed this mammoth volcano to build up layer upon layer of solidified lava in the same location for millions of years. This process, combined with Mars's lower gravity, about 1/3 of Earth's, enabled the volcano to grow to heights impossible on our home planet. To truly grasp the scale of Olympus Mons, consider this. If you were to stack 3 Mount Everests one atop another, you still wouldn't reach its summit. The volcano's slope rises so gradually that if you were hiking from its base to its peak, you might not even realize you were walking up a volcano. The grade is so gentle because of the low gravity and the highly fluid lava that once flowed down its sides, spreading out over vast distances before cooling. The volcano's caldera, or crater at its summit, is itself a wonder of planetary geology. This complex depression consists of multiple overlapping craters, each up to 80 kilometers across, testifying to repeated cycles of volcanic activity and collapse. The walls of these craters drop away for up to 3 kilometers, offering a window into the volcano's internal structure and history. Around the base of Olympus Mons lies a distinctive feature known as the escarpment, a cliff up to 6 kilometers high. Scientists believe this formed as the immense weight of the volcano caused the Martian crust to bow downward, creating a moat-like depression around its base. This same tremendous mass may have also helped prevent the type of catastrophic eruptions that we see in Earth's volcanic systems, instead favoring slow, steady outflows of lava that built up the mountain over time. Recent studies suggest that while Olympus Mons is currently dormant, it might not be completely extinct. Some surface features indicate volcanic activity could have occurred as recently as 2 million years ago, practically yesterday in geological terms. This raises intriguing possibilities about residual heat and potential subsurface water systems that could be valuable for future Mars exploration and potential colonization efforts. Valles Marineris stands as the most spectacular canyon system in our solar system, a colossal gash in Mars's surface that dwarfs any comparable feature on Earth. This Grand Canyon stretches an astonishing 4,000 kilometers across the Martian equator, a distance that would span from New York to Los Angeles if placed on Earth. Its depths plunge up to 7 kilometers, creating sheer cliff faces that could completely engulf Manhattan's tallest skyscrapers, with room to spare. The formation of this massive canyon system remains one of Mars's most intriguing geological mysteries. Scientists believe it began forming over 3.5 billion years ago through a combination of tectonic rifting and subsequent erosion. As Mars's crust split apart, the initial fissure was gradually widened and deepened by a variety of processes including ancient groundwater movement, landslides, and possible surface water flow. The canyon's walls reveal distinct layers of rock that serve as a timeline of Martian geological history, each stratum telling part of the story of the planet's evolution. Evidence of past water activity abounds throughout Valles Marineris. Satellite imagery has revealed mineral deposits consistent with ancient lakes that once filled portions of the canyon. These minerals include water-altered clays and sulfates that could only have formed in the presence of substantial amounts of liquid water. Side canyons and channels branching off from the main canyon system suggest extensive water erosion, while massive landslide deposits indicate that water may have periodically destabilized the canyon walls. Recent observations have detected seasonal dark streaks on some canyon walls, suggesting that even today, small amounts of liquid water might occasionally flow just beneath the surface. These features, known as recurring slope lineae, have made Valles Marineris a prime target for future exploration missions, seeking evidence of current water activity on Mars. Your turn to join the exploration. Which of Mars's incredible geological features captures your imagination the most? Is it the towering heights of Olympus Mons, or perhaps the mind-bending scale of Valles Marineris? Share your thoughts in the comments below. Your fascination with specific features helps us understand what aspects of Martian geology most intrigue our audience, allowing us to craft future content that delves deeper into the topics you find most compelling. The search for water on Mars represents one of the most significant quests in planetary science. Compelling evidence from multiple Mars missions reveals that liquid water once flowed abundantly across the red planet's surface. Valley networks, remarkably similar to Earth's river systems, branch across vast regions of the Martian surface, strongly indicating sustained water flow over extended periods. These ancient waterways range from small stream beds to massive outflow channels that dwarf Earth's largest rivers. Mineral deposits discovered by orbital spacecraft and surface rovers tell an equally compelling story. Spacecraft have identified vast deposits of hematite, clay minerals, and sulfates, materials that typically form only in the presence of liquid water. The Curiosity rover's analysis of rocks in Gale Crater revealed smooth, rounded pebbles characteristic of sustained water transport, similar to rocks found in Earth's riverbeds. These water-worn stones provide tangible evidence of ancient Martian streams. Recent discoveries have revolutionized our understanding of present-day water on Mars. Radar observations have detected large subsurface lakes of liquid water near the South Pole, preserved by high concentrations of dissolved salts that lower the freezing point. The Mars Reconnaissance Orbiter has also identified recurring slope lineae, dark streaks that appear seasonally on steep slopes, potentially indicating contemporary water flow just beneath the surface. These water discoveries hold immense significance for future human missions to Mars. Water will be essential for life support, providing drinking water and oxygen through electrolysis. It can also be used to produce rocket fuel for return journeys through hydrogen extraction. Understanding the distribution and accessibility of Martian water resources is therefore crucial for selecting landing sites and establishing sustainable human outposts. The presence of subsurface water could also reduce the amount of water future missions need to transport from Earth, significantly decreasing mission costs and complexity. The ongoing hunt for Martian water continues to yield surprising discoveries, each finding bringing us closer to understanding Mars's watery past and its potential to support human exploration in the future. Mars's polar regions present a striking display of seasonal change and hold vital clues about the planet's climate history. The polar caps consist of two distinct layers: a permanent deposit of water ice mixed with dust, overlaid by a seasonal layer of frozen carbon dioxide, dry ice, that grows and shrinks with the Martian seasons. The northern cap spans approximately 1,000 kilometers, while the southern cap measures roughly 3,000 kilometers in diameter during winter months. The Martian seasonal cycle drives dramatic transformations at the poles. During winter, temperatures plummet to 125 degrees C, causing atmospheric carbon dioxide to freeze directly onto the polar caps, creating a layer of dry ice up to 2 meters thick. As spring arrives, solar radiation triggers sublimation of the dry ice, releasing pressurized gas that carves distinctive spider-like channels in the polar terrain. This seasonal freeze-thaw cycle also influences Mars's atmospheric pressure, causing it to vary by up to 30% throughout the Martian year. Beneath these frozen caps lie intriguing discoveries. Radar observations from the Mars Express spacecraft revealed evidence of liquid water lakes buried beneath the South Polar ice cap. The largest of these subglacial lakes extends approximately 20 kilometers across and lies about 1.5 kilometers below the surface ice. These lakes likely remain liquid despite freezing temperatures due to high concentrations of dissolved salts and the pressure of overlying ice. Similar to subglacial lakes in Antarctica, these Martian lakes could potentially harbor microbial life, protected from harsh surface conditions by their icy shield. The polar deposits also serve as a climate archive, preserving layers of ice and dust that record millions of years of Martian climate history. Each layer represents a snapshot of past environmental conditions, allowing scientists to reconstruct how Mars's climate has evolved over time. Analysis of these layers suggests that Mars has undergone significant climate changes driven by variations in its orbital tilt, similar to Earth's ice ages. Perhaps the most profound discovery about Mars's past lies in mounting evidence that a vast ocean once covered much of its northern hemisphere. Satellite data and surface geology suggest this ancient ocean contained around 20 million cubic kilometers of water, comparable to Earth's Arctic Ocean. This revelation fundamentally changes our understanding of Mars's potential for past life and its climatic history. Topographical analysis shows a clear dichotomy between Mars's elevated southern highlands and lower northern plains, with the boundary resembling ancient shorelines. Advanced mineral mapping has identified widespread deposits of clay minerals and other water-altered materials across this region, consistent with long-term exposure to a large body of water. The timing of this ocean's existence coincides with when Mars was most Earth-like, approximately 4 billion years ago. The planet then possessed a thicker atmosphere and a magnetic field capable of retaining this substantial amount of surface water. As Mars lost its magnetic field, solar radiation gradually stripped away its atmosphere, causing the Northern Ocean to evaporate or freeze and sublimate into space. This ancient ocean would have created conditions remarkably similar to early Earth. featuring a complete hydrological cycle with precipitation, river systems, and seasonal variations. The extended period of stable liquid water on the surface significantly increases the probability that Mars once harbored life. Evidence suggests this ocean may have existed for hundreds of millions of years, ample time for potential biological processes to emerge and evolve. The ultimate fate of this ocean's water remains an active area of research, with some potentially trapped in subsurface ice deposits or bound within hydrated minerals, while a significant portion was lost to space. Understanding this transformation from a wet to dry Mars provides crucial insights into planetary climate change and the long-term habitability of worlds beyond Earth. The exploration of Mars's geology and ancient water history has direct implications for humanity's future on the Red Planet. Our understanding of Martian resources, particularly subsurface water deposits and mineral concentrations, will prove crucial for establishing sustainable human settlements. These natural resources could provide essential materials for life support systems, construction, and fuel production through in-situ resource utilization. The geological features themselves offer potential locations for human habitation. Lava tubes and deep canyons could provide natural radiation shielding, while subsurface ice deposits could supply water for drinking, oxygen generation, and hydrogen fuel production. The presence of hydrated minerals throughout the Martian surface also presents opportunities for water extraction using relatively simple heating processes. Terraforming possibilities, while challenging, stem from our understanding of Mars's past climate. The planet's poles store significant quantities of frozen carbon dioxide and water ice that, if released, could contribute to atmospheric thickening. However, current calculations suggest that all available CO2 on Mars, if released, would only increase atmospheric pressure to about 1.5% of Earth's sea level pressure, far short of human requirements. More practical near-term approaches focus on localized habitat environments rather than planetary-scale transformation. Understanding Mars's geological history helps identify regions with accessible resources and favorable conditions for establishing protected habitats. Regions with evidence of recent subsurface water activity, such as recurring slope lineae, merit particular attention as potential settlement sites. The distribution of useful minerals, identified through our study of Mars's geology, will influence future mining operations. Iron oxides are abundant across the surface, while sulfate and clay deposits indicate locations of other valuable minerals. These resources could support manufacturing of construction materials, life support systems, and even rocket fuel components. Knowledge of Mars's past climate changes also provides crucial insights into maintaining long-term settlements. Understanding how the planet lost its atmosphere and water helps engineers design more resilient habitat systems and potentially develop strategies to protect against similar degradation in artificial environments. The surface of Mars serves as an unparalleled geological archive, revealing the remarkable tale of a planet that once closely mirrored Earth. From towering volcanoes to deep canyons, each feature tells part of an epic transformation from a warm, wet world to today's cold desert. Through detailed study of these formations, we've uncovered evidence of ancient oceans, flowing rivers, and potentially habitable environments that existed billions of years ago. This understanding extends beyond mere scientific curiosity. Mars's geological history provides crucial insights into Earth's possible future and the delicate balance of conditions necessary for maintaining a habitable planet. The dramatic climate change that transformed Mars from a water-rich world to its current state offers valuable lessons about atmospheric loss, the importance of magnetic fields, and the long-term evolution of planetary environments. As we contemplate human expansion into space, Mars's geology takes on practical significance. The locations of ancient water flows help identify accessible ice deposits, while understanding mineral distributions guides resource utilization planning. Each geological discovery brings us closer to making sustainable human presence on Mars a reality. Join our vibrant space exploration community by subscribing to Exploring the Universe. We'll explore the icy surface of Europa, the volcanic fury of Io, and the possibility of subsurface oceans on these fascinating worlds. Each discovery across our solar system adds another piece to the puzzle of our cosmic neighborhood.